Today we will review the basics of network flows that we started last time. So we will go over I'll just quickly review the augmenting path algorithm, the maximum-Minkert theorem. I'll just review the proof of the maximum-Minkert theorem. And then most of our time we will spend on applications of network flow. Okay. Quiz 4, originally it was scheduled for Tuesday, and then we changed it to Friday because we wanted all of you to finish your problem set before we have the quiz. But then it turns out that there are some students who cannot even attend class on Tuesday because it conflicts with an exam. So we're going to have quiz 4 on Tuesday, and this is quiz 4. This basically tests your understanding of the algorithms for shortest paths and network flows. So it won't ask you to develop an algorithm for a new problem. It will test your understanding of the algorithms that we have studied. So specifically, the algorithms you should be familiar with would be how Dirichlet algorithm works, how Bellman-Ford algorithm works. This is single source path. Then we have covered all pair shortest path, and there is an algorithm that uses the matrix multiplication approach, and then we covered Poisson. And then the fourth person algorithm for okay. So, and I presume that all of this you will be doing anyway for your problem set, so this should not be more burden. I know some of you, I think there was a posting saying that there is another exam on Tuesday for many of you, but there are no conflicts, so I think it's impossible to schedule it on a date when other people can't even attend. So, okay, any questions about the quiz? Yes.
So not about the quiz.
Yeah.
About the exam. Are we going to cover another topic after network flow? Like
We will cover NP completeness. There won't be any questions in the exam on NP completeness. There may be like a bonus question possible. That's what we have done in the past. I don't know whether we will. Okay. So for the final, so since we're talking about the final would be cumulative. So it will be for the entire course, except you can be assured that there will be more weight given to the second half of the course. So you can surely expect a problem on network flows. You can expect a problem related to dynamic programming. You can expect problems related to graph reversals, possibly greedy algorithms, and okay. Any other questions? Okay. Okay. So recall the network flow problem. The network flow problem in its sort of most basic form is you have a directed graph G with capacities on every edge. Okay, and these are integer capacities, and you can define the problem with non-integer capacities as well, although the problem takes a different form and funny things happen. So we will assume that all the capacities are integers. Then you're given a source and a sink T, and the goal is to find flow of maximum value from S to T. Okay, what is the flow? Recall that a flow is simply an assignment of numbers to each edge. Okay, it just says how much stuff is going across the edge. What should it satisfy? It should satisfy capacity constraints. That is, for every edge, the flow should be less than equal to the capacity of the edge. And by the way, this should not be Z plus, meaning it allows zero values, of course. Capacity, and then you have the conservation constraint. That is, if you look at any node other than the source or the sink, whatever goes in has to go. Okay, E going into vertex V. Look at all the edges that go into a vertex V. Add that up. Add the flows. This should be exactly equal to all the edges going out of V. And you add it up. For V, that is not equal to S of V. Of course, for S, there is something going out, and for T, there is the same amount going in. So the value of the flow given by V of S, that's precisely equal to the sum of the flow leaving the source. Okay, and we made several observations, and we proved some of them. So we observed that, if you look at any cut, okay, and again, whenever we talk about a cut, we talk about a cut with S on one side, T on the other side. Okay, even though we won't say it all the time, remember a cut in a network flow problem is S. One side should have S, the other side should have T. If C is any cut, then the net flow across the cut is exactly equal to the value of the flow. Net flow across cut equals. What is the net flow across the cut? It's the flow going from the S side to the T side minus the flow going from the T side to the S side. Okay. Okay, so one implication of all of this is that the value of the flow is exactly the same as if you count the stuff going out of S, or the stuff going into T, or the stuff going across any kind of One other lemma is called weak duality, is that the value of the flow is less than equal to the capacity of any cut. Okay, what's the capacity of a cut? It's the total weight of the total capacity of the edges going from the S side to the T side. What's the capacity of the cut? It's the summation over all the edges going from the S side. So let's write down the cut C as two parts, S and T. Capital S is the stuff, it is a set of vertices containing the source S. Capital T is a set of vertices containing sink T. So E from, that's the capacity. Okay? Okay. So we did all of this. So now let's just remind you of the algorithm as well as the max flow length theorem. Okay, so the fourth Fulkerson augmenting path algorithm is initially you start with a zero flow and then you repeatedly build the flow by finding an augmenting path, including that, finding the residual graph, and then repeating. Okay? So initially, the flow F of E equals 0 for all. Okay, your residual network, when you have sent no flow, is simply the original graph. While there is an augmenting path P. An augmenting path means any path that has positive capacity. Any path that is positive capacity. While there is an augmenting path P from F to T in GF. Okay. Notice that GF is the residual network. Okay. Stent flow of let C be mean capacity along path F, along path P. Send flow of C along P. Update residual network. Yeah. And then you just repeat. Okay? So recall what happens when, let's say you identify this path Let's say this had, you were sending, let's say you were sending 3 units of flow out of a capacity of 7, suppose. And you are sending 2 units of flow out of a capacity of 3, 1 unit of flow. Okay. So there are other edges also here. And so on. Okay? But you're looking at this part. Let's say this is your augmenting part. So this is your, so if this was the flow being sent on these edges, in the residual network, what would happen? You would have an edge, so let me give names to it, A, B, C, D. In the residual network, you would have A, B, C, D. You will have an edge from A to B, whose capacity would be 4. But you'll also have an edge from B to A with capacity 3. You'll have an edge from B to C with capacity 1, but also a capacity this with capacity 2. C to D, capacity 3, and this with capacity. Okay? Now, if you chose this to be your path, your augmenting path, okay, in this stack, let's suppose you chose that to be your augmenting path. How much flow can you send along that path? 1. So the value of C in this iteration would be 1, because the minimum capacity, the maximum you can possibly send is the minimum capacity of the edges that you have. So it's just 1. Okay? So if you were to send 1 unit of flow in the residual network, how will you update it? So you will increase the flow along this edge to be 5. Sorry, not increase the flow along this edge to be 4. Increase the flow along this edge to be 3. Increase the flow along this edge to be 2. So you will update your flow F, and you will update your residual network. How does the residual network get updated? Okay. So now, if this has increased from 4 to 3 to 4. This has increased from 2 to 3. This has increased from 1 to 2. So your residual network will have 3. This edge will vanish because this edge has 0 capacity now. Then this edge will have 2 residual capacity. This edge will have 4 residual capacity. This edge will have 3 residual capacity. So in the residual network, GF becomes like this. Okay? And then you just repeat. You again find an augmenting path in this graph, and you just keep it. Okay? Okay, so that's this algorithm. We saw an example, a very simple example, that this algorithm will take a long time in the worst case. Why? Because you might repeatedly pick the wrong path. But it turns out there are just variants of this, while here we have said pick any augmenting path. Okay, so let me make a note of that. So just remember that Ford-Fulkerson is more like a framework. This is a generic algorithm. It doesn't specify how to find these paths. Okay? You could use anything to find this augmenting path. What could you use to find an augmenting path?
DFS.
You could use DFS, you could do BFS, you could do sort of any kind of exploration. So Ford-Fulkerson is a generic algorithm. It turns out, if you were to actually use BFS, so that you always try to find the shortest path, the path that has the fewest number of hops, that works very well. Okay? that variant of the algorithm where you is called Edmonds-Karp, because they came up with this idea. And so that's generic algorithm. In the worst case, may have value of flow iterations. In the worst case, what might happen is that every round, every iteration, the flow will increase by 1. Okay? So every round, the flow will increase by 1. So it will terminate because it will keep on going, and at some point it can't add any more, so it will stop. However, that may take a long time because the number of iterations could be enormous. The value of the flow could be enormous. Edmonds-Karp, where you always try to pick the shortest path, that is actually guaranteed to end in time, I think, order E times V iterations. And each iteration itself just takes you linear time. So the overall running time is something like E squared times V, or V squared times E. I don't exactly know what it is. I think you can do it in V squared times E, but okay. But basically the point is that this algorithm is guaranteed to complete in polynomial time, only dependent on the size of the graph, not dependent on the actual value of the flow. Okay, so even if the graph is of size 100 vertices, but the value of the flow is 1 billion, this will just take time proportional to, dependent on the size of the graph. Okay? Yes?
So when you say DFS is shortest hop with the weights?
No, not DFS, BFS.
So DFS with the weights instead of, it's not like the shortest one?
No, it is the shortest hop, no weights.
Oh, okay.
Literally BFS. Yes. So don't look into weights at all. Okay. Don't look into capacity at all. Okay. Now you could, instead of, when you want, this just looks at the augmenting path that has the fewest number of hops. You could instead say, okay, I'm going to always pick the path that can send the maximum amount of flow. Okay? So I could find a path that has the maximum bandwidth. Okay, this is almost the same as your problem set question. How to find a path that has the maximum bandwidth. That you could also do that. So instead of the Edmonds-Karp, just okay, the generic algorithm does not say anything. Pick any augmenting path. Edmonds-Karp says pick the augmenting path that's equal to that has the fewest hops. You could also say, instead of that, pick augmenting path that has the largest capacity. Okay? So that has the largest capacity. That is also a good algorithm. This will also complete in some time like this. Okay. Intuitively, it makes sense that you always try to push as much flow as you possibly can. That's what this tries to do. From our standpoint, we are not going to try to analyze why these finish fast. Meaning certainly you can see that on that particular example, if you had that particular example we had constructed, where we had 1 million capacity on this, all of these had 1 million capacity. Okay. If you were to do the generic Ford-Fulkerson algorithm, you might mistakenly take this path, and then this path, and you go on for 2 million iterations. Instead, if you were to do the Edmonds-Karp, where you take the shortest path, the very first path you would take is this. So you would send 1 million units on that, then the next path you will take is this. You will send a million units, so that you'll be done. If you were to take the augmenting path that has the largest capacity, again, you would choose one of these two paths, and then you will be done. Yeah?
So would you, so let's say we were going to do Edmonds Park, would you compute all of the shortest paths prior to the while loop, and then?
No, no.
Okay.
Good question. You are always trying to find the shortest path in the residual network,
Right.
and which is keeping on changing.
Yeah.
So you do it every time. So you find the shortest path first on the graph, then you make your change, and then you find again. I mean, there might be smart ways to find the shortest path. And actually, it turns out that you don't really need truly shortest path as long as you have a good enough path. It works. But there are a lot of heuristics so network flow is so widely used that you need really fast algorithms, and these algorithms, even though they are polynomial time, if the algorithm takes E times V times V and you have like 1 million vertices, that's a huge amount of time. So from a practical standpoint, even this algorithm is not good enough. Okay. So there are lots of ways people have found out to make these algorithms faster. In fact, just 2 years ago, there was, or maybe more than 2 years ago, there was a beautiful result that showed that you can find almost optimal flows, not optimal, but almost maximum flows in almost linear time, using completely different techniques. In fact, viewing network flows as electrical networks and things like that. So it's a really fascinating area. But I think the point is, from our standpoint, network flows can be solved. Okay, and you need to know the basic idea between flows and cuts. We need to know that there is some way to solve it. And whenever we are trying to solve other problems using flows, we can simply claim that, oh, we already know how to solve network flows. We'll just use code. Okay. Yes.
When there's multiple, when T has multiple degrees or ways to produce a flow going into it, how does the scheduling work of that?
So when T has multiple things coming in,
right?
And so good. So your question is sort of outside the scope, in the sense that your question is, how do you, let's say we were actually in a position of, we have calculated the flows. So it tells you that 2 units is coming from here, and maybe 3 units are coming from here. How do you, when the units actually flow, how do you schedule these 2 units versus these 3 units? Right?
I think as well, like if you were to occupy a couple of units in one path,
yeah,
can you reoccupy that again with the flow, or does it have to direct the unit somewhere else?
Good. Okay. So, so the question is, what we have calculated in these flows is how much is flowing on what edge, and the next question you could ask is, how did these flows actually happen? Okay, that's in some sense an orthogonal question. Okay, it's the same question as saying, let's suppose on the internet we allocate bandwidth along the path. And so what does bandwidth along the path means? That means that, okay, we're going to send 10 megabits per second. We have allocated space for this connection, 10 megabits per second along this link, 10 megabits per second along this link, and so on. Now when the actual packets come along, how do I figure out which packets to be sent when? That's a different problem. A scheduling problem is different from a flow problem. Okay, and usually what happens is you basically have some kind of a router sitting at each of these nodes, and that router has to make sure that it has input queues, output queues, and when the input queues come in, it wants to make sure that it can work at the same rate at which things are coming in. So so that's a different problem, and scheduling packets or scheduling connections and scheduling flows, often you can, whatever you can do using this network flow, whatever you have determined, you can realize it, okay, in the scheduling process. Okay, any other questions? All right. So that's so as I mentioned just now, that the main thing to keep in mind is how the network flow algorithm works. That there is a way to solve this problem in polynomial time, and in particular, there is a way to solve this problem in E squared beta using Edmonds curve. Okay. Okay. So let's. As we discussed last time, that in fact we have talked here that by weak duality, and the reason it's called weak duality will be clear in that the maximum flow cannot be. Is at most the minimum cut. That's what weak duality shows. The maximum you can send is at most the capacity of the minimum cut. The maximum in-cut theorem actually says that in fact these two are equal. That you can always send as much as what the bottleneck allows you to do. Okay, and the proof of that, I'm going to sketch it. It basically uses what we have done already in the Ford-Fulkerson algorithm. So. So the value the value of the maximum flow is exactly equal to the value of the minimum cut. Okay. Okay, so the basic idea behind that theorem is we've already shown the value of the flow is less than equal to the value of the minimum cut. Now the way we will argue that the value of the flow is actually equal to the minimum cut is we will argue that when the time this algorithm stops, at that time the value of the flow is actually equal to the minimum cut. So it cannot be bigger than that. And so that's essentially the proof that maximum flow is equal to the minimum cut. Okay. So when Ford-Fulkerson terminates, when this algorithm terminates, the value of the flow is equal to the capacity of some current. Okay. And the idea is that when Ford-Fulkerson terminates, what's happening is you have a source here, you have a sink here, and you look at all the so when does the Ford-Fulkerson algorithm terminate? When there is no path from source to sink. That means let's look at all the vertices that the source can reach. Let's mark them as one side. And look at all the vertices that the source cannot reach and mark them as the other side. what does that mean? That means every edge that is going from here to here now has capacity. How much capacity does it have? 0. Okay. So if it has capacity 0, that means how much flow does it have? Going across. 0. Well, how much flow does it? Remember, this is the residual network, right? Remember, this is the residual network. Okay? So, in the original network, how much flow is going across the site if this has capacity 0 in the residual network? It has as much flow as its capacity, right? Because in the residual network, if there is no capacity, then it must be the case that in the, remember how do we calculate the residual network capacity? I took it out. You look at its capacity minus the flow. So if the residual capacity is 0, then the flow on that edge is equal to the capacity. Okay? Good. So every edge that is going from here to here in the original graph has 0 capacity in the residual network. That means the flow on each of these edges in the original graph is equal to the capacity. Okay? Alright. What about an edge going in the reverse direction? How much flow is going on an edge on this reverse direction? Okay? So let's say this had a capacity of 5. I don't know. Okay, let me step back. So, so far you agree that the flow along every edge going in this direction, from this S to this T, is exactly equal to the capacity of the edge. Okay? So what is the net flow from here to here? Well, the net flow from here to here is the sum of all the capacities of these edges. But I have to subtract any flow that is going from here to here. Well, let's look at an edge going back on this direction. So this edge has capacity 5 in the original. How much flow could possibly be going across this?
5.
Well, you can have as much as 5. Except, remember, if there was any flow going on this, in the residual network, what will happen?
There's some going in the
Well, if there was a flow, let's say, of 2 units going across this in the original graph, what will the residual network have? It will have an edge going from here to here of capacity 2. But there is no edge of capacity, any capacity in the residual network. So there could possibly not be an edge going in the carrying flow in the reverse direction. Okay? So the value of the flow across this cut is exactly equal to, so net flow across cut is exactly equal to capacity. Okay? So notice that since weak duality says that net flow, the value of the flow is no more than the capacity of the cut, and we have found out a cut whose net flow matches, then this must also be the minimum cut, right? Because max flow is no more than the minimum cut, but we have found a cut where max flow is actually equal to that cut, then this cut better be the minimum cut. Okay? So this basically proves, once you have identified one cut such that the net flow across the cut is equal to the capacity of the cut, this implies max flow. So it's important to remember that the Ford-Fulkerson's augmenting path algorithm can be used not only to find the maximum flow, it can also be used to find a minimum cut. Because all you need to find a minimum cut is identify the vertices that are reachable from S in the residual network at the point at the end. That will be your one side. Not reachable will be the other side. Okay? So max flow algorithm. Okay? This notion of maximizing something and minimizing something, they're actually very interesting duals of each other. The reason the term duality comes up here is the fact that maximizing flow basically is equivalent to minimizing cuts. Okay. In one direction, and this comes up often and again in economics. I mean, this duality arguments come up again and again in economics and many areas of computing as well. Okay. We won't be able to dwell on that other than the application here. Okay, so we have gotten sort of a high-level view. And now let's quickly review some good applications of perhaps the simplest application is that of bipartite matching and variety of examples in the bipartite matching space. Okay, we will do at least two right now. So we went over stable matching. So in stable matching, we were looking at the case where we had one set of items trying to be matched to other sets of items, and there are preferences and so on. But let's formulate a different version of it. Let's say you had a bipartite graph. So one set of vertices, A, and another set of vertices, B. Okay? And your goal was, remember in the original stable matching problem, everybody gave up an ordering among everybody else. But maybe in practice you can't have that, or maybe you don't know because many of these men here may not know any women there, or many of the women there, and vice versa. So let's formulate the problem differently. Let's say you had edges indicating you are willing to be matched. Okay? These edges indicate that this vertex is willing to be matched to this vertex, to this vertex, and to this vertex. So this edge is willing to be matched to any of these three vertices, but should not be matched to any of the other vertices. Okay? What's a matching in this context? It's exactly the same. It's a set of edges such that one side on the left is only matched to exactly one side on the left. Okay? And now let's ask the following question. Let's say we want to find the largest line. So is the problem problem clear? In this graph, you have vertices on the left, A, vertices on the right, B. I want you to pick a matching, which means match vertices on A to vertices on B, such that you're able to match as many vertices as possible. Okay? And it may not be possible to match all the vertices, because maybe the number on the left is not the same as the number on the right, or maybe some people were not liked by anybody or something like that. Okay? So how would you go about doing this? Now you might be tempted to come up with some, maybe a greedy algorithm kind of an approach, where we might say, all right, I'm going to just assign this one to this one, then I will try to find, for the next vertex, I will try to find one of the vertices available, and so on. You can try some of those examples, and you'll basically fail. Okay. But it's almost immediately possible to do this using network flows, even though the problem seems to have nothing to do with network flows. There is no talk about flow, there is no talk about cuts, but this is actually just a network flow problem. Okay. How? So the way you would attack this problem is you would say, all right, let me have add a source here and a sink here. Okay? I add a source and a sink here, and I attach edges from here to here and edges from here to here. Okay? So what we're going to do is going to be basically, this is what we are going to present, is a reduction from the bipartite matching problem to the network flow problem. Okay? So what we're doing is reduce bipartite matching to maximum flow. Okay, what does the reduction mean? Given an instance of the bipartite matching, I'm going to produce an instance of the network flow problem. What does an instance of the network flow problem consist of? It consists of a directed graph. It consists of a source, a sink with capacities on all the edges. So I've built a directed graph. Okay, I'm going to have the source here, the sink there, all the edges like this, and I'm going to make all the edges here directed like this. All the edges go between A and B, go left to right. Okay? I make everybody's capacity 1. Okay? Now I'm going to claim that a maximum flow from S to T will give me a maximum matching in the original graph. Okay? Maximum flow is equivalent to how do you establish that? The way we'll establish this is we'll say that, okay, if you give me a flow, I'm going to extract a matching. If you give me a matching, I'm going to show you a flow. So flow corresponds to matching, matching corresponds to flow, so maximum flow has to be correspond to a maximum matching. Okay? So there are 2 parts. For every flow, I will get you a matching. Of the same value. So let's look at a flow. Let's look at any flow of value f, of let's say value v. What does the flow look like? Well, the flow has to consist, so let's look at a flow. A flow consists of, it gives you some numbers for each of these edges, right? So for some edges it will have a value of 1, for some edges it will have a value of 0. Okay, we are going to assume that this is all integral flow. because you're only working with integers. So it gives you a value of 1, value of 0. Okay. So look at all the edges here that have a value of 1. Ignore the edges that have a value of 0. So this edge is the value of 1, this edge is the value of 1. So that means if this edge is the value of 1, by flow conservation, what happens? One of these edges should have value of 1, because 1 unit of flow is coming in, 1 unit has to go out. And in fact, exactly one of them should have a value of 1, not more. So if it's a valid flow, then one of the edges. So let's say this edge. And that means this edge, there is exactly one edge leading. That has to have value of 1. So that means the flow is nothing but, this cannot happen. Okay, this cannot happen. Why is that? 2 units cannot reach there. Right? So flow has to look like a set of disjoint parts going from S to T, going through one vertex here and one vertex here. That exactly corresponds to a matching. What's the size of the matching? Exactly the size of the flow. Okay. Similarly, if you were to give me a matching that only matches one vertex here to one vertex there, I can build you a flow of exactly the same size by just connecting, sending flow according to that. So this is almost sort of trivial. Both of these are trivial observations. If you give me a matching, it implies a flow of the same value. Okay? So, what does this mean? This means that you can solve the maximum matching problem by instead solving the corresponding maximum flow problem. And it turns out that you can do faster than just running the flow, but that's not really about it. But basically, you know how to solve maximum matching using the flow. Okay? Okay, let's look at a variation of that problem. Let's say assigning jobs to servers. Okay. So let's say you have the following problem. You have you're given n jobs and m servers. Okay? You're given n jobs, m servers. Each server has a capacity. So each server I has a capacity Ci, which means it can only take Ci jobs. It can only do Ci jobs. Capacity Ci means it can no more. It cannot do more than Ci jobs. Okay? For each job, you have a set of possible servers. For each job j, you have a set Sj of possible servers that can serve it. And you need exactly one of the servers to serve it. Okay? Question? is there a way to assign the jobs so that all of them get completed? Is the question clear? Yeah.
It can do CI jobs at a particular point of time or?
No, totally. Yeah. You can only assign CI jobs to it. And you cannot assign any job anywhere because the job only has a certain set of servers that could possibly go. Okay? So I'd like all of you think about it. So essentially what all of you should be thinking about is, can I write this out as a network flow problem? In particular, can I build a picture like this? Okay, and essentially once you have the right picture of the network, it's very, it should be immediate. Okay, again, is the question clear? Okay, you have n jobs, m servers. Each server has a certain capacity. Each job has only a certain subset of the servers it can go to. And is there a way to assign? How will you solve this using network flows? Okay, the first attempt would be, the first thing you should try to do is make a bipartite graph. So let me okay. So it's natural to try this. You put all there are two entities. You have to assign jobs to servers. So you put jobs on one side. And let's say there are n jobs. So I put all the jobs. And then you put the servers on the other side. M server. Okay. What do you do next? Yeah.
So we put the source and the sink.
Okay. So you put a source here and the sink here.
From the servers to the sink will be the capacity.
From the servers, so from each server.
Each server to the sink.
So let's say this is the server I to the sink. You could use the capacity. How many jobs can it take? Okay, so let's stop there for a moment. So each of these, so this is capacity C1, this is capacity C2, and so on. Okay? What should we do between the jobs and the servers? One. So which job should have an edge? So this job should have an edge to which servers?
Everything.
Everything in its set S1, because it cannot be assigned everywhere. So that's where S1 appears. So it's difficult to indicate, but basically this corresponds to the set S1. In general, Sj, this is Sj. Corresponds to the Sj. It only has those edges to those servers which are in SJ. Okay? So how will you write it formally? You will say add an edge j to I if I belongs to SJ. Okay? Add an edge from the job j to server I if I is in the set of servers that j can do. What capacity should you put for the edges inside? In this 1, because each job basically is just 1 unit. It just counts towards 1 unit. Okay, it remains to connect the source to the jobs. So each source will connect to every job. What's the capacity of each of these? 1. Okay. Now our claim is simply that max flow on this. So now what do we want to find out? We want to find out, is there a way to assign the job so that all jobs get completed? What's the corresponding question here? Yeah, total flow equal n. Is the total flow equal to n? Is the maximum flow equal to n? So the question we're going to ask is the maximum flow equal to n? So why are they the same question? Well, the same question. They are the same question because we have a claim that there is an assignment with k jobs if and only if there is a flow value k. That is, every assignment of k jobs corresponds to a flow of value k. Every flow of value k corresponds to an assignment. Okay. And it's the same argument that we did there. Okay. If you give me an assignment, if you tell me that this job is going to be placed here, this job is going to be placed here, then I will just construct a flow exactly using those jobs and those servers. If you give me a flow, an integer flow that is not doing fractions, but if you give me an integer flow where you assign k, you send it k units of flow. So those k units of flow have to be k jobs. Each of those jobs can only be placed in servers because of these edges, servers which are allowed to complete them, and then you get a k. Okay, and when you have n units of flow, that means every single job here is assigned. So you answer your original question: is there a way to assign the jobs? Okay, no question? Yes.
I'm just confused. What happens if the capacity of the servers is less than the number of jobs?
Correct. So then very good question. So what will happen if the capacity of the servers is less than the number of jobs? Then the answer would be the maximum flow will not be equal to n. Why is it? Because remember, this cut, what is the capacity of this cut? Is the total capacity of all the servers. So if this cut happens to have value less than n, then we know that max flow can never increase, can never be more than the capacity of any cut. So the max flow will be less than n. So the answer to that question would be no, you cannot assign. But that's not the only reason, by the way, right? It's possible that the servers might have a lot of capacity, but there might be something funny going on with maybe there are lots of jobs that can only go to these two servers, but their capacity might have been less than the number of jobs. So then there will be a very different cut. Yes?
So I'm just trying to understand a little bit better. Is it a one job to one server deal? Or
No.
multiple jobs?
Multiple jobs can be assigned to the same server, though one job will be only assigned to one server.
So couldn't you do this with almost a greedy algorithm too?
Okay, go ahead.
You sort in descending order
Of what? Of capacity?
of size of jobs and
No, jobs are all the same size, just one unit.
okay. And that makes okay.
The-
And then descending order and size of servers, and then you allocate jobs until you can't allocate it to the server, and then you move on to the next, and then if you get to the end and all the jobs haven't been allocated, then return false.
So here is the problem. So let's say you have a server. So if you're starting with the server that has the most capacity. So let's say a server has capacity of, let's say this is the capacity of 3, this is the capacity of 2, this is the capacity of 1. Okay? And let's say these are jobs, 4 jobs, and let's say this job can only be assigned to this server. Okay? Then, and this job can be assigned to this server, this job can be assigned to this server. But these 2 jobs can also be assigned here. Let's say this is your picture here.
Okay, so there's specific paths, meaning that jobs can only be assigned to certain servers.
Yes, that's what SJ is.
Okay.
Yes. That's it, that's exactly. That's the, and the problem is, you in your greedy algorithm, you cannot, you can try to do some other heuristics such as, oh, I'm going to try to assign that job that has very few options. But then you run into other problems. Okay, because it might have few options, then there will be 2 jobs that might have few options, and which ones to pick. But their options, it might have few options, but those options may not be congested. So what do you do? So we are trying to figure out the bottleneck. And the kind of bottleneck we are looking for is exactly the bottleneck that Max will open. Okay, so let me do one more. That is similar. You're given a directed graph G. Okay, and you're given a source S. And this thing T. Or destination T. And many times you want to, in many situations, whether this is in the context of transportation or in the context of routing, communication, you have a source, you have a sink or a destination. You want to find paths that do not overlap. Okay, so you want to find paths that are disjoint. And we will focus our attention on paths that are edge disjoint, and they can share vertices, but not edges. So you want to find maximum number of edge disjoint paths from S to T. Okay? Again, what does it mean to say that 2 paths are edge disjoint? Well, 2 paths are edge disjoint when they don't share any edges at all. Okay, and so all the paths we are looking for should be completely, they should not share any edges. So no edge should be shared by more than one path. Okay? So that's the problem. How do you solve this problem? Well, this is almost immediately solved by the maximum flow problem. You take the graph, so you reduce the maximum flow. How do you reduce it to maximum flow? Well, you simply build the maximum flow with the same graph. Use the same graph G. Set all capacities to 1. Set all edge capacities to 1. And then solve a maximum flow. T. Since all capacities are 1, when you find the final flow and you return it, then you simply start from any S and look at any edge that carries the unit flow and just keep following. It will have at least one more edge out of it that's carrying the unit flow. This will have at least one edge carrying unit flow. This will have at least one edge flow, and you keep doing it. You would have found one path carrying corresponding to a flow of 1. Then you do the same thing with the next path. Basically, any flow can be decomposed. If the flow value is V, it corresponds to V versus time points. Okay? No edge will be used by more than one part, because remember, each edge only has a capacity of 1 and it can only carry a flow of 1. So either it carries a flow of 1 or 0. If it is 0, it's not being used. If it is 1, it's being used by exactly 1 part. Okay? Yes?
Like if when we reduce the problem to a network flow problem,
Yeah.
so like in exam, should we ask the complexity? So should we write it as V square?
Yes, you can write down if the complexity, there are two parts to the complexity. One part is the construction of this graph. So you should describe how long it takes you to construct the graph. Then your VE squared, if you were to refer to the Edmonds Karp algorithm, the V and the E correspond to the vertices and the edges of the graph you have constructed. Right? So yes. So the running time would be the time it takes to construct plus the time it takes to solve the flow. Usually the construction is much less than the time it takes to construct the flow. So the flow is the one that counts. But the running time of the flow is a function of the number of vertices and edges in the graph that we are constructing. Okay? Right? Okay. Okay, so the final problem is the project selection problem. This is a different kind of a problem, and then that we have seen. And you'll actually use a different. You will use the notion of min cut, and it's really a clever use of min cuts. Let me set the stage of the problem first. And again, at the face of it, it seems to have nothing to do with cuts and flows. Okay, so the problem is you are given a set of projects. Okay? You're given a set of projects. And these projects have dependencies. And these dependencies are captured in a DAG, in a directed acyclic graph. That before you do this project, you must have done this project. Before you do this, you must have done these two, and so on. So you have a DAG given to you. May not be entirely connected. So you have all these projects, okay? that your company wants to work on. Okay? But of course, they only have a small amount of resources, and the resources are in terms of people they have, and they also calculate the benefit that you might get from each of these. So for each of these projects, you have figured out what would be how much value you get. So the value of the project. The value of the project is by itself, so it will be determined by when you complete the project, how many resources you're putting in, what revenue you're going to get out. And if you subtract them, you subtract the revenue minus cost, that's your benefit. So for each of these, you come up with a benefit. So this is, let's say, vertex 1, so you come up with benefit B1, vertex 2, B2, 3, 3. But this quantity could be negative. If the cost incurred is higher, then it could be negative. But why you may still be interested in doing it. Why? Because even though it's negative, why may you still be interested in doing this? Because it may enable other projects that are very high revenue. Okay? So you might still be interested, but you don't know. So, but at the same time, there might be some projects that might be valuable, but then if you get the value out of it, and it opens up other things. Okay. So now here is the problem. I give you this whole chart with all the positive numbers and the negative numbers and so on. I would like you to figure out what projects are you going to do so as to maximize your revenue. Is the question clear? Okay, so BI equal to revenue I minus cost of I, and BI could be positive or negative. So 0. Okay? Now you have to figure out what set of projects to maximize benefit. But remember that we do have to satisfy precedence constraints. We do have to satisfy precedence constraints. Okay? And the precedence constraints are basically that before you can do this 3, you must make sure that you must have done 1 and 6, otherwise you cannot do it. Okay. Now, we will go over, so again, at the face of it, it seems like, oh, maybe you could do something else. You could do some greedy procedure, dynamic programming, but there is really a beautiful algorithm using min cuts. It seems to have nothing to do with the problem. The idea is what we will do is, we will put this in a network flow graph with a source and a sink, and then we will find the min cut, and we'll argue that the min cut of that graph, let's say the source, is the set of projects that you should do, which will give you the maximum value. Yes?
So it's fairly obvious what your source is going to be, right? It's going to be the node coming at you, right?
There could be many of them.
Well, wouldn't you want to pick the node that has known dependencies before it?
Correct. So you could say that it's not clear. The construction will be, you will create a source, you will create a sink, and you will you're right in the sense that you can connect the source only to the original sources that are there, that is just coming in.
Okay, right.
You could do that, but then you'll have to figure out how much, you'll have to capture this benefit. Where do you put this benefit in? Okay, so you will actually have a different construction. You will, I think we'll go over this in the next class in more detail. Yes?
One, is this a little different in the sense that all of the source nodes have to be complete for the following nodes. So for instance, for 3, both 1 and
5 has to complete.
right.
So 1, 5, 6 has to complete, but notice that you don't have to complete this. Yeah. Okay, I think I'm going to stop now. Yes?
I was going to ask you to go ahead, doesn't matter.
Go ahead.
I just don't understand the point of the edge disjoint paths. Trying to accomplish.
Okay, so the question is edge disjoint paths. So edge disjoint paths are needed, for example, let's say you're trying to route traffic, and you might want to find paths that don't share anything, because if they don't share anything, then please don't get. I'm going to return the midterm, so the edge disjoint paths are ways to find more reliable paths.
I was kind of out there.
So I just wanted to review So I just wanted to quickly go over the midterm problem, some of the problems, not all of them, but some of the problems. So the first problem was on this is a graph, the safe nodes problem. So you're given a directed graph. And the question was find all nodes. So a node is, a vertex V is safe, or U is safe, if every vertex that it can reach, every vertex V such that U has a path to V, also has a path back to U. Okay, safe problem. And there are two parts. One was giving an example, and so the idea here was that simply that what you want to find out is are vertices that if they can reach somebody, then they have to be able to reach them. Okay? And so one way to do it is to do DFS. You can run DFS from U, figure out all vertices it can reach, and then do a DFS in the reverse graph to find out all vertices that can reach it. If they exactly match, then U is safe. If they don't match, then U is not safe. And that's expensive because you're running too many. The faster way to do it is to find the strongly connected components. Once you find the strongly connected components, the vertices that are safe are the ones that should not be able to go outside that component, because if they go outside that component, they can never return. So these are exactly the vertices in the sink components. Okay. Mistakes some students made were they were sometimes looking at components that have more than one vertices. But notice that if a vertex in this graph, okay, let's suppose this is the graph. How many safe vertices does it have? One. This vertex is safe. It cannot go anywhere, and so there is no vertex that it can go to. So it can just stay there. So basically, the definition of safe is every vertex V such that it can reach can come back. Okay, so this was an SCC question. The second question was on minimum spanning trees. One was on finding. just running Kruskal's algorithm. I think just running Kruskal's algorithm, most of you got it, but there are a few people who did not get it. But really, these are problems that you should understand the basic of the algorithm and make sure to solve it. Okay, I'm not going to go with the second part. The third question on greedy algorithm for greedy algorithm for the weighted waiting time. You needed to prove that the order in which you have to be doing things is you pick the vertex, pick the client that has the smallest value of Ti over Wi. And once that is proved, what's the algorithm? It's trivial. You just sort all the clients according to this and pick the one and put them in that order. So the part B was almost immediate. You just have to do n log n for sorting. But how do you prove that this is the right order? Well, the proof is basically if you look at the optimal solution and it did not have this order, so it had two clients where one was I, one was J, but I was before J in the order, but it turned out that Ti over Wi happened to be greater than Tj over Wj, and this was before. Then you observe that for clients before and clients after, what you're going to do is you're going to swap them, and clients before do not change, clients after do not change. But when you swap them, its waiting time, I's waiting time increases by Tj. J's waiting time decreases by Ti. So effectively what happens is you increase by your total cost increases by, so I's waiting time has increased by Tj, so Wi Tj, that's the increase, but then you decrease minus Wj Ti, but this is less than 0. Okay, because this is the same thing as, we know that Ti by Wi is greater than Tj by Wj, so you multiply this, Ti Wj is greater than Wi. Okay, so this quantity is strictly less than 0. So when you make the swap, you actually improve, so this must imply that the original optimal schedule was not really optimal. The fourth one was on dynamic programming, and I think a number of you gave, there were actually at least 2 or maybe 3 different ways to write the dynamic program. One was just with 1 variable, one was with 2 variables, and a number of you gave good approaches, if not the exact correct algorithm. The mistakes people are making often was, if you're writing a recurrence, I noticed that sometimes in a recurrence, one side would have 3 variables, and then the other side will only have 2 variables. So if you're ever writing a recurrence in which it doesn't seem to match, that's a problem. So you should try to identify that. Okay, I think I'm actually going to do, I'm going to call out names. So this will take a little longer. And this is in first name order, so you know when to wait. Okay, Aaron Cancer. Aaron Moskowitz. Aditi Kateria. Aditi. Aditi Kalalka. Aditya Prasad. Aditya Thakur. Aditya Thakur. Akash Parikh, Amitesh Deshpande, Anand, Anna, Andrew Pierce, Andrew, Athanas Pablo, Atul, M. Atul, Atinder Pal Singh, Azman, Bhargavi, Bing Chi, Bo Tan, Bo, Brad Keenan, Cornelius, Devna, Cynthia Perry, Chintan, Christopher, Cole Clark, Dash Desai, David Hara, David Sarowski, Dipanshu,
Yeah, sorry for that. No worries, thanks.
Dipanshu, Double Deria, Double Milind Molankas, Dishari Bhattacharya, Duo Jan, Dweer Gogia, Erika Krishna, Forrest, Gabe Bishop, Gaurav Jain, Gautam Gajal, Guanju Zhang, Hanisha Udani, Harish Ramani, Harsh Modi, Harsh Mehta, Harshil Jain, Hashmeet Johal, Hassan Khan, Himanshu, Puichi Mao, Ibrahim, Jerry Lani, Yahoo, Jiachin Shi, Jiaxuan Wu, Joseph Triolo, Joseph Vele, Josh, Kathleen, Kushbu, Liu Zhang, Liang Zue, Liang, Li Peng Hao, Lee Metati, Lipi Mehta, Lixi, Manisha Sharma, Mansi Jain, Matthew, Maxwell King, Mayuresh, Mixing Dong, Mihir, Mitali Shroff, Mingshan Lee, Mohini, Mohit, Monica Subramani, Naga. Oh, this is two Nagas. Naga Durga and Naga Sai. Nandita, Nikar Gaurav, Noah, Olivia D'Angelo, Parth Kotak, Pablo, Pallavi, Parth Barhampur, Peranchi, Prachi, Pratiksha, Preeti, Chiwan Ram, Raj Kukaria, sorry, Rajat, Rishabh, Ritika Gupta, Rohan, Ronit Sharma, Ruichan Ram, Ryan De Silva, Samarth Parik, Sanjay Badlani, Sara Hopus, Sasan Vishwanathan, Satvik Sabarwal, Soumya Shah, Saurabhi Jirgi, Saurabh Jirgi, sorry. Said Shiva Yogi, Shresh Bhatnagar, Shreya Dharan, Shreyan Jasoria, Simran Dhaliwal, Smruti Ramesh, Soumya Bhargav, Song Lee, Srinivasa, Sumit Sankhi, Sumit Gajar, Surya Menon, Tao, Tejas Patel, Teng Zhang, Timothy Sakharov, Utkarsh Pujari. Teng Vaibhav. Venkat Satya. Viha Vidre. Vinayak Raman. Viral Pandey. Viral Patel. Brenton Liu. Will Foster. Chi Zheng. Chi X-I. Jiangxi Jiangxi. Jiaowei Mei. Jin Chao Shang. Jin Chao. Zilmin Dong. Zubo Tan. Yang Wu. Yexin Wang. Yixin Zhang. Zenda Wu. Average 19.9, median 20.
And I was wondering like, if you could put up on that what you did last time.
Now when you have that, yeah, that's just part of it. I had to last night and all my I know, I had to